All right, let's look at some rules for antiderivatives. The first one I want to look at is the power rule for antiderivatives. And really, this is based off of the power rule for derivatives. Remember, when you take the derivative of x to the n, you know what you get is nx to the n minus 1. So, what we do there is we multiply by n and then subtract 1 from n. Multiply by the exponent and then subtract 1 from it. So to do the antiderivative, we're going to do the opposite of those two things, and we also have to switch the order that we do them in. So the general antiderivative for x to the n is this. If you look at this, what we do is we take this x to the n, we add 1 to the exponent, and then we divide by that. So you get that 1 over n plus 1 times x to the n plus 1 plus the constant. And that only works when n is non-zero. Or, I'm sorry, when n is not negative 1. Because if n were negative 1, what would happen here is you get 0 up here, which that's not a problem, but this over here is. So if n is negative 1, if n's negative 1, you're looking at 1 over x. And what is that the derivative of? Natural log. So the thing to remember here is, the main thing is this part of the rule. And you might even want to think of it as x to the n plus 1 over n plus 1 plus c. So I want to do several examples of this. The first example I want to look at is this guy here, number 1. So we've got x cubed plus 3x minus 4. All right, so when I take the antiderivative, this one becomes x to the 4th over 4. Then we get 3 times x gives us x squared over 2. And 4 just gives us 4x. And then we always have to add that plus c on there when we're finding general antiderivatives. So we could leave it like that, or I guess we could rewrite it as 1/4 x to the 4th plus 3/2 x squared minus 4x plus c. And that's all there is to it. All right, example 2 here. This one really it's really the same, but we're going to have fractions in it because that x is raised to the 1/2 power. So first up, rewrite this as x to the 1/2. And so when we get our antiderivative, which I'm going to call capital G, let's see, you get x to the 1/2 plus 1. Then you have to divide by 1/2 plus 1. Then add your c on the end. So let's look at this. That becomes x to the 3/2 divided by 3/2. But don't leave it like that. It's kind of ugly to have this double fraction. So dividing by 3/2 is the same thing as multiplying by 2/3. So rewrite this as 2/3 x to the 3/2 plus c. And keep in mind, you can always check these. If I take the derivative of 2/3 x to the 3/2, you can always check these by taking the derivatives. Let's see, what do we get there? We get 2/3 times 3/2 x to the 3/2 minus 1. And notice I didn't even put the c in there because derivative of c is 0. And so this gives me just x to the 1/2. So you can always check these by taking the derivative of your answer, and you should get the original thing back. All right, this one actually we can't do. We can't do this one yet. I mistakenly put it in there. What we can do, though, is this. I'm going to rewrite, I'm going to make a new problem here. 3x to the squared plus 4x minus 5 over 12x. If we're given this one we can do. And the reason is we can split this into three different fractions. We can rewrite this as 3x squared over 12x plus 4x over 12x minus 5 over 12x. And before we do any antiderivatives and stuff on this, what we can do is simplify each of these. So h of x is, let's see, this first one becomes, this becomes x over 4. I'm going to call it 1/4 x. The next one just becomes 1/3. And then the last one, I'm going to write it as 5 over 12 times 1 over x. All right, so the antiderivative of this, for this 1/4, the 1/4 stays out front. And then I get x squared over 2, or multiply it by 1/2. 1/3. If we take the antiderivative of that, we get 1/3 x. And this one down here, we get minus 5 over 12 times the antiderivative of this is natural log of absolute value of x. And I'm going to combine some stuff together here. This one's going to give us 1/8 x squared plus 1/3 x plus 5/12 natural log absolute value of x plus c. All right. Now, these are all using the power rule for antiderivatives. But we have a bunch more antiderivative rules. If you look at this, this is just a partial listing. Basically, what we've got is a bunch of these for each of the derivative rules that we've learned. So the antiderivative of e to the x is just e to the x plus c. The antiderivative of cosine is sine plus c. The antiderivative of sine is negative sine. Oh, that's a mistake. I didn't proofread this very well. The antiderivative of sine is negative cosine x plus c. The antiderivative of 1 over 1 plus x squared is arctan plus c. I throw this one in there because this comes up a lot in calculus too, so it's important to memorize that one. Now, I left off a few things, like I could have put in the antiderivative of secant squared is tangent. I left that off, but you know, every one of those rules that we learned for a trig function derivative, there's a corresponding rule for antiderivatives that goes backward. Let's see. We saw this one above. 1 over x, if you take the antiderivative of that, you get ln x plus c. And technically, that should have some absolute value bars on it. All right. Now this one right here, if we just have a constant, we've seen this a few times. If you have a constant and you take its antiderivative, you just get the constant times x and then plus c. And these last two rules tell us that taking the antiderivative is a linear operation, meaning if you've got two functions added together, you can take their antiderivatives independently. And if you've got a constant times a function, you can take the antiderivative of the function and leave the constant on front. We've been using both of these rules on all these examples, but we just haven't talked about them explicitly. So anyway, that's those are the rules, and we'll pick up on initial value problems in the next video.